Welcome back to NoelCule. Today we're going to talk about how AI researchers built models so big they literally broke their computers, and the surprisingly simple factory trick they used to fix everything.
Okay, so let's get right to it with the big question. When we're talking about AI, does size actually matter? Is bigger really better? Is all this effort to build these enormous models even worth it?
Well, the research says yes, a resounding yes. And what's so cool about this is you're looking at two completely different jobs for an AI. On the left, we've got image recognition. As the models get more parameters, you can kind of think of them like more brain cells. Their accuracy just climbs and climbs. Same deal over on the right with language translation. Bigger models, higher scores. The takeaway is crystal clear. If you want a smarter AI, you've got to build a bigger one.
But, and this is a huge but, that leads to a massive problem. Researchers basically hit a brick wall, a literal physical wall. The AI models they wanted to design were just so huge, they couldn't possibly fit into the memory of a single computer chip, like a GPU. They had the blueprint for a skyscraper, but only a single car garage to build it in. It just wasn't going to work.
So what do? Well, the first idea was pretty straightforward. If one garage isn't big enough, hey, why not use a few more? And this leads us to the first most obvious solution, a simple, but as we'll see, a really inefficient assembly line.
So the approach is called model parallelism. You can see it here. You just split the AI model into different steps, and you put each step on a different computer chip. So chip 0 does the first part of the job, then it hands its work off to chip 1, chip 1 does its part, passes it to chip 2, and so on and so on. Just like a car factory. Worker 1 puts on the wheels, worker 2 installs the engine. Sounds logical enough, right? Well, here's the catch, and this graphic shows the fatal flaw perfectly. While chip 1 is busy working, what are chips 0, 2, and 3 doing? Absolutely nothing. They're just sitting there, waiting for their turn. They're idle. The paper calls this dead time bubbles in the pipeline. It's like having most of your factory workers on a coffee break at any given moment. It is incredibly inefficient, just a massive waste of really expensive computer power. And this is where the big breakthrough happens. The researchers had this aha moment. They realized this wasn't really a hardware problem, it was a workflow problem. They just needed a smarter assembly line.
So they called their solution GPipe, and the big idea behind it is something called batch splitting pipelining. Now, let's stick with our factory analogy. Instead of trying to build one giant car all at once, what if you broke the job down? What if you sent dozens of small go-karts down the assembly line, one right after another? In AI terms, that's what they did. They split one big chunk of data into lots of tiny micro batches. And just look at the result. It's night and day. By sending all these little micro batches through, those bubbles just vanish. As soon as the first chip finishes its tiny task, it passes that little piece of work to the second chip and immediately starts on the next piece of work. All the chips are busy all the time, working in parallel. The assembly line is just humming along. The efficiency, it just goes through the roof. Okay, so with this new super efficient factory for building AI, what could they actually create? Well, the results are genuinely mind-blowing.
First up, they built an image classification model with 557 million parameters. Now, just to put that into perspective, a cutting-edge model from just a few years before might have had around 60 million. So this is a massive leap forward. And all that size directly translated into raw performance. This absolute monster of a model set a new state-of-the-art record on the ImageNet challenge. That's kind of like the Olympics for image recognition. It was simply more accurate than anything that had ever come before it. But of course, they didn't stop there. They wanted to see just how far they could push this. So next, they built a language model with a staggering 6 × 10 billion parameters. And what do you do with a 6 billion parameter AI brain? You teach it to become a universal translator for over 100 different languages. Now here's the part that really gets me. This single giant model that learned everything all at once, it was actually better than specialized models that were trained on just one pair of languages at a time. It's like, by learning over 100 languages at the same time, it developed a deeper, more fundamental understanding of language itself. Okay, so we've seen bigger models, better results. But let's zoom out. What's the really big picture here? Why is a technique like GPipe so fundamentally important for the future of artificial intelligence? Well, it really comes down to 3 huge advantages. First, it is incredibly efficient. This basically means if you double your number of computers, you almost double your speed. It just scales. Second, it's super flexible. This isn't a one-trick pony. It works for a massive range of different AI models. And finally, and this is so critical for doing good science, it's reliable. The training process is stable and consistent, whether you're splitting the job into 4 pieces or 40. It just works. What this technique really did was give researchers an infinitely scalable assembly line for AI. It just removed a fundamental roadblock to progress. It means the size of our AI models is no longer limited by a single computer chip, but only by our budget and our ambition. Which leaves all of us with one final, very exciting question.